Good morning. So, at the end of last lecture, we were looking at beta decays. In particular, we were looking at what's called beta minus decay, and we were looking at beta minus decay for carbon-14. So, we were looking at this, everything outlined here. We said that the carbon-14 is observed to decay into nitrogen-14. We said during that decay, there's a high energy electron coming out, there's a high energy neutrino coming out, which took a long time to be observed. Neutrinos are really hard to observe, so when these decays were first being observed, the neutrino was missed. And what researchers wondered about was there was always a missing amount of energy. There was energy that could not be accounted for. And so the first concern was, well, isn't energy conserved? Now, if we also look at the angular momentum of the reactions, people observed that in beta minus decay, angular momentum wasn't being conserved, nor energy, nor momentum. It seemed like all the conservation laws were being broken. And what Enrico Fermi suggested was, well, there's probably a particle that we're missing. And Enrico Fermi suggested that that particle would be neutral because it wasn't leaving a track through their bubble chambers. The particle would be neutral, it would be really low mass, and it would be carrying away a significant amount of the energy of these decays. These neutrinos are so difficult to detect. It was like 20, 25 years later until the first observations of the neutrino were made. But now it's well understood. We have 50 years or 60 years of neutrino observations now that we have in place. And we understand that the neutrino is a particle related to the electron. It's the neutral version of the electron in some sense. And that through the weak force that we can generate particle-antiparticle pairs of the electron and neutrino, and that's what's happening in beta minus decay. So a neutron is turning into a proton. The weak force requires that another particle-antiparticle pair be generated at the same time, and so the electron and the neutrino. So these are all particles that did not exist in the carbon-14. The nitrogen is gone, the neutron is gone, replaced by a proton, and then these are two new particles coming out. Also in the previous lecture, we went through, we counted the protons, neutrons, electrons, and we carried out the Q calculations and were able to come up with a Q value of 0.1556 MeV, so it's not terribly energetic. You could ask, well, how dangerous is this? If I'm if I have something that's undergoing beta minus decay, am I at risk from that material? And let's see what the risks would be. This is fairly low energy, and half the energy is being carried away by the neutrino. Now, neutrinos are pretty safe. Neutrinos only interact through the weak force, and the weak force it's really weak, which means that the neutrinos just pass through things. So if you had a radioactive decay that happened within you or nearby, the neutrinos we just wouldn't be worried about. The electron, though, is a concern. A high energy electron coming out at these type of energies could cause a lot of damage. Same with the alpha particles. The alpha decays that we saw, now the beta decays that we're seeing, these high energy particles coming out break chemical bonds. So an electron coming out with a lot of energy could break a number of chemical bonds before it comes to rest. Now, carbon-14 is one of those naturally occurring radioactive materials. It has a half-life of almost 6,000 years, and it's generated through high energy particles coming through our atmosphere. So there are high energy particles that come through the atmosphere that convert nitrogen into carbon-14, and then that carbon-14 chemically ends up forming into carbon dioxide. So about 1 in every trillion carbons in the carbon dioxide in our atmosphere is carbon-14. It's radioactive. And so there's this steady process of maintaining the carbon-14 at this level. It's about 1.3 parts per trillion. That means that inside of you, about 1 in every 1.3 in every trillion carbons is radioactive. So hey, you're radioactive, right? And that's because of the CO2 that is made up of carbon-14 in the air. That CO2 gets used by plants and incorporated into the plant. The plant makes sugars, they make lipids, they make proteins, they make nucleic acids, all using carbon without regard to whether it's carbon-14 or carbon-12 or carbon-13. And so that small fraction of radioactive carbon is present in all living organisms that are actively metabolizing. If you're actively taking in new sources of carbon, either out of the atmosphere, as plants do, or by eating the plants, as animals do, then you've got that certain fraction of radioactive carbon-14. Another naturally occurring radioactive isotope is potassium-40. Turns out potassium-40 has a half-life of like 1 billion years. And so there's leftover potassium-40 from the formation of the solar system. So the solar system formed from leftover debris from supernova explosions. And in those supernova explosions of high-mass stars, a certain amount of potassium was present, and some of that potassium was radioactive potassium-40. It's still around. And so we are, we're exposed to small amounts of carbon-14 and small amounts of potassium-40. I remember when my kids it's kind of like when my kids went through second grade, part of the teaching in second grade was talking about, I guess, radioactivity. And sure enough, the kids would come home from school and say, "Dad, we got to stop eating bananas." And I go, "Really? Why are we not eating bananas anymore?" Because they have potassium-40 in them. That's hard to get around. I mean, if you stop eating bananas, you got to get potassium from somewhere. And whatever source you're getting your potassium from, there's going to be that small amount of potassium-40 present. So it's something that, through the evolution of life on Earth, there have always been these low levels of carbon-14, potassium-40 present, and all organisms have ended up with mechanisms that allow survival in an environment where you have this, fraction of radioactive isotopes present within the organism itself. So you've got enzymes running back and forth along DNA strands, checking for small errors. So if you have a radioactive decay, it's very likely, if you catch it quickly, like with carbon-14, you can take that base out of the DNA and that'll get replaced. So there's a system of enzymes that run through the DNA looking for signs of errors. They can identify errors, replace that base with a new one. Proteins get recycled. So if damage occurs in a protein molecule, well, eventually all the proteins are being recycled anyway, and new proteins will be built. So, those processes are in place. It's part of the living experience here on this planet and other planets as well. All right, carbon-14, beta-minus decay, calculating the Q values. All right, let's look at, this is just a slide on neutrinos, talking a little about neutrinos, and not too much new information here. Here is the antineutrino that's been produced. Now, here's another example of beta decay. So this is beta plus, and it's just a different example. Here is a radioactive isotope of neon, and it's neon-19. And neon-19 radioactively decays into fluorine-19. And again, It's like saying, hey, the neon is already really stable, but there's something it could easily turn into that's even more stable. And then down here is another example. So this is beta plus, this is beta neutral. We want to look at both of those in detail. So you should understand all three types of beta decay really well. These are good examples to pay attention to. Notice that we're getting neutrinos in each of these. We're getting an electron here, not here. And the electron we get here it's not your standard electron. It's actually an anti-electron. It's what's called a positron. It's a positive version of the electron. So let's take a look at these reactions one by one and outline what's going on. So first of all, it's the weak force again. So in all of these beta decays, we're bringing in the weak force. And we have another one of those Feynman diagrams. But in beta plus decays, instead of a reaction where a neutron turns into a proton, we have a proton turning into a neutron. And we had said before, that's another one of the possibilities. So a proton turns into a neutron. Now here's the weak force in this case, and the weak particle, the particle that makes up the weak force, is called, well, there's three. There's a W plus, a W minus, and there's a neutral Z. Those three particles are all part of what we call the weak force. Now in this case, again, we're going to end up with an electron and a neutrino, but if we take a look at the charges here, the proton's bringing in a positive charge. The W has a positive charge on it, so this time instead of having an E minus, a regular negatively charged electron, we're going to have a positron, the positively charged anti-electron that comes out. Now if this is the antiparticle, then this must be the particle. So in beta plus decay, instead of getting an anti-neutrino, we're getting your regular old standard neutrino that's coming out of here. So let's outline this reaction. I wrote the reaction up, neon 19 goes to fluorine 19, and then I wrote in the underlying reaction, which I think really is a helpful way to think about these. So I've got a proton turning into a neutron, and from particle physics, elementary particle physics, we know that an electron plus and a neutrino are going to come out. Now those particles that are generated, they're going to carry away most of the kinetic energy of this decay. So in beta plus and beta minus, most of the energy is being carried away by the electron and the neutrino. So I've counted the number of protons and neutrons, and neon 19, that's element number 10, that's 10 protons, 9 neutrons, and if it's starting out neutral, it would also have 10 electrons. And again, the electrons that we have here, they're spectator electrons. These electrons are not getting involved in the decay process itself. That's not what's happening here. So these are just spectators. And what's happening in the nucleus is one of the protons is turned into a neutron. That says instead of 10 protons, we're down to 9, but the number of neutrons has gone up. So we have the same mass number, the 19 hasn't changed, but the atomic number has decreased by 1. And that makes it fluorine, and it makes it the 19 isotope of fluorine. And as far as fluorine is concerned, having 10 electrons that's too many. So those 10 spectator electrons are one more electron than what fluorine would have if it were neutral. So I want to charge balance and put a minus sign here. Now, I feel like for some reason physics textbooks don't keep track of the charge balancing very well. Chemistry textbooks do such a nice job on this. But charge balance is important because we don't want to miscount the number of electrons. We'll be off. The Q calculations, which we want to get to, we want to be able to carry out a Q calculation for this, those are going to be off significantly if we miscount our numbers of electrons. So I'm checking everything looks charge balanced. Once I get that plus sign in place, And that says, for this beta plus decay, that I'm going to be taking the mass of what I started with, which is the neon 19, and subtracting off the mass of the fluorine, mass of the electron, mass of the neutrino. And with the fluorine, I have to remember to add the mass of one additional neutron. One additional electron. So the mass of the fluorine, mass of the electron, mass of the neutrino. Now we can ignore the neutrino. Its mass is so low. But that extra electron on the fluorine is significant. So what that's going to become is the mass of a neutral fluorine, 19. And I've got one mass of an electron here, plus an extra one here, because that fluorine's got one extra electron on it. And that gives us 2 electron masses. So calculating Q's for beta plus requires us to take the mass of the 2 nuclei, or the 2 atoms, neon 19, subtract off fluorine 19, but we also need to subtract off 2 electron masses to do the balancing correctly. So that was different from beta minus. In beta minus, we didn't have to include 2 electron masses. For beta plus, we do. We've got to make sure those are in there. Now, I looked up all the numbers. It turned out that the mass of neon 19 is 19.001881. The mass of fluorine 19, 18.998403. Those both round to 19.0. In fact, 19.00. So you can see their masses are really similar. And I'm going to need a lot of significant figures to pick out the small difference. And then I had to include 2 masses of electrons, so I included those in. This is what I ended up with, 0.002380 atomic mass units of missing mass. That's going to give me my Q value. So I can multiply that by 931.5, and that gave me 2.217 MeV as an energy of decay. This is fairly energetic. Now we're getting up to a little over 2.2 MeV. That's a higher energy beta plus decay. So, what are the concerns if I were to be exposed to something that's beta plus decaying? What are the concerns? And well, again, the high energy neutrinos, no big deal. The high energy neutrinos just pass right through me. Very, very unlikely that they would interact with anything at all. The E plus, however, that's a high energy electron, and that's going to be able to break chemical bonds. Then there's a second concern with the E plus, and it's an anti-electron. So even when this positron slows down, let's say it zips through my molecules and breaks hundreds of chemical bonds, and then it finally slows down, then what happens is the E plus is going to react with one of my other electrons and generate 2 high energy photons. So the entire mass of the positron and the entire mass of one of my electrons will get converted into high energy photons. So that's another MeV. That's like a half MeV, a half MeV. They get converted into photons. That's like adding an additional MeV into the energy of the decay. So a second concern with having antimatter being produced inside me, or being exposed to a little bit of antimatter. All right, I guess that finishes out everything we want to say here. Okay, so beta plus, make sure you understand these sorts of reactions also. I'm going to put that on my high priority list. And then the third type of radioactive decay that we mentioned, beta decay, that we talked about, is what I'm going to call beta neutral decay. So beta neutrals, I'm writing a little 0 up here, decay, it actually goes by the name of electron capture, But, well, it's been a few years back now, but I have a student one time that said, hey, we could call this beta neutral. And I kind of liked that. So I think we got to spread that around the physics community or whatever and see if we can get people to start calling it beta neutral. So we had beta minus, beta plus, and now beta neutral, which is electron capture. And here is the example of a radioactive material, beryllium-7. Beryllium-7 is not stable, or it is stable, but there's something more stable that it can easily turn into. And the something that it can turn into that's more stable is lithium-7. So, but in this reaction, we don't have an electron coming out from the nucleus. We only have the neutrino. And hey, the neutrinos are safe, right? The neutrinos aren't going to cause any damage. So how is it possible in this beta decay that no electrons are being produced? And in this case, well, here's our Feynman diagram. Here's the proton turning into the neutron. Here is the weak W particle mediating that reaction. In this case, instead of producing an electron, it uses one of the electrons as a reagent, something going into the reaction. And where this electron gets picked up from is from the beryllium atom itself. So the beryllium has 4 electrons attached to it, and the 1s electrons have a significant overlap with the nucleus. So in this case, when the proton turns into the neutron, that is coupled to a reaction which takes one of the indigenous electrons and turns it into a neutrino. So it uses one of the electrons within the beryllium itself. Now I should have done this. I did not do a proton, neutron, electron count here, over to here. But in this case, since we're using a proton and an electron, both already present in the beryllium, there is no electron that's coming out the other side. To calculate the Q values for this reaction, we can take the mass of the beryllium and subtract off the mass of the lithium and subtract off the mass of the neutrino. Now the neutrino has basically no mass, so we can ignore that, and we really just have to look up these two numbers. So I did that. I went to Appendix F, not the periodic table, went to Appendix F and got the masses specifically for the 7 isotope of beryllium and the 7 isotope of lithium, and there they are. So I took this mass and subtracted from this, but wait a minute, did we charge balance? So let's go back and think, what would charge balancing look like in this reaction? Now, I started off with 4 electrons in the beryllium. This time, not all the electrons are spectators. One of the electrons actually reacts. And so I started with 4 electrons, but I only end up with 3 electrons for the lithium, and that says, oh, the lithium's fine. Since the reaction took away one of the protons and it took away one of the electrons at the same time, the charge balancing is taken care of. And we can kind of already see that. The neutrino has no charge, and so we started with something with no charge, the neutrino has no charge, the remaining nucleus should have no charge on it, the remaining atom should have no charge on it either. So beta neutral, electron capture, we ended up with these numbers for the 2 atoms before and after. Here is the missing mass, 0.000926 atomic mass units. Here is our conversion from mass into kinetic energy. And it turns out that's 0.8626 MeV. You guys can check my numbers on these too. So I'm highly recommending that you practice these examples on your own. So check my numbers. If you find any discrepancies here, let me know. And I can update those update my numbers. All right, so that's the amount of energy that's released. The bulk of that energy coming out in the neutrino. Neutrino is perfectly harmless. Okay. All right, that's our third type of beta decay. Now, the way the textbook writes the beta decays, these always concern me a bit. Let's see how this works. This is beta minus, which they have in parentheses over here. So we start with some nucleus. So here's the chemical identity or the chemical symbol. Here's the number of protons. Here's the total number of, or the mass number. And notice in all of these beta decays, the mass number never changes. And that's because the nucleon number that we have inside stays the same. If I've got a nucleus and I turn some of the protons into neutrons or some of the neutrons into protons, the mass number doesn't change. So those top values are the same. Now what we did see in beta minus decay is that the number of protons increases by 1. And in beta plus decay, the number of protons drops by 1. So I've got Z becomes Z plus 1, Z becomes Z minus 1. Now the other items that we saw here are an electron and an antineutrino coming out for beta minus decay, an anti-electron and a neutrino coming out for beta plus decay. All right, so far so good. I think those work pretty well. The last one is the one that I guess I have the most concern about. Don't let this get you confused. I would highly recommend taking your notes and just cross out that electron. Because if I say I have an atom coming in and I add an electron, it sounds like the electron's coming from somewhere else. But where is that electron actually coming from? And that electron is coming from within the atom that's represented by that symbol. So cross that E minus out, maybe put a parentheses underneath, like we did, put the underlying reaction there. But something's got to tell you that the electron that gets used, that reacts, is already present in the atom. See, otherwise, I look at this and I think, that's not charge balanced. Well, these weren't charge balanced either. So we were more careful with the charge balancing. Let's see, this is going to have a plus on it, and this is going to have a minus on it. Those would be good items to correct also on these. So this is going to come out with a plus, this atom is going to come out with a plus sign, this atom is going to come out with a minus sign. Cross out the electron here, and in the case of electron capture, or beta neutral, the remaining atom that comes out is already neutral. It's not going to have a charge on it, and then the only high energy particle coming out is the neutrino. All right? So maybe update those or make sure you understand. It's not uncommon to see on a midterm or something, students working with this and adding an additional electron and getting the Q calculations incorrect. All right, gamma decay. So we did alpha, we did beta. Beta was really fun. There were those 3 different types of beta decay, and we got to see protons and neutrons turning into each other, and we got to introduce the neutrinos too. Gamma decay is a high energy photon that gets generated, and gamma decays occur after an alpha or a beta decay has taken place. What they're outlining for us here, this is boron 12. And boron 12 is radioactive. Boron 12 can turn into carbon 12, and carbon 12 is more stable than boron 12. So this reaction takes place at some rate. Now, there's a couple possibilities here. The boron 12 could beta decay directly into carbon 12. Now, that's an enormous Q value. Boron 12 kind of has way too many neutrons to it. So it's, I don't know what the half-life is here, but that's a really large Q value. So it can undergo a beta decay directly into the ground state of carbon 12. And that would release all the kinetic energy immediately in that reaction. But all of these nuclei have not just their ground state, but they have excited states. And so here's an excited state of carbon-12, the carbon-12 nucleus, and you go, what's an excited state mean? Remember, we got these protons and neutrons in these different quantum states. So for carbon-12, I got 6 protons, I got 6 neutrons, and I got pairs of protons and neutrons spin up and spin down in the lowest 1s states, and then there's going to be some 2s states and some... so what's happening here is when the decay first occurs, not all the protons and neutrons have settled into the lowest available quantum states. So I've left a proton or a neutron in an excited state, and then at some later time, that can decay. Often it's pretty immediate. So what this is showing is that we can start off with an electron in, the boron 12 can decay into an excited state. And in this case, the beta decay releases 9 MeV, and then that final readjustment of the protons and neutrons into the lowest state releases an additional 4.4. That's pretty considerable, right? That's a 4.4 MeV photon given off when a nucleus drops from an excited state into a ground state. And quick question, does carbon-12 and carbon-12 excited state have the same mass? And it turns out they don't. Excited states have more mass than ground states do. Excited states have more energy, and so they actually have a higher mass. Now, when we think of that in nuclear terms, that's pretty significant. 4.4 MeV is going to be a measurable amount of additional mass. This is going to be significantly heavier than its ground state. But we can also apply this in chemistry situations. Going back to atoms, we could say, all right, which has more mass, the ground state of an atom or an atom where one of the electrons is in an excited state, and the excited states have a little bit more mass, right? So there are small variations of mass even in atomic systems depending on whether the electrons are in excited states. A hydrogen atom in the ground state with the electron in the ground state versus a hydrogen atom with the electron in a, the 2s or the 3s or 4s or 5s. Each of those higher energy states is going to have a little bit more mass. In those cases, the difference in energy is only 13.6 eV, so it's not as significant as the differences in masses for these nuclear states. But that's a pretty significant difference in mass. Okay, again, this is gamma decay. Gamma decays can be outlined just in terms of the gamma decay that's happening here is between this excited state and this state here. Now, we could have gone in and calculated individual kinetic energies on this one too. I don't have a separate example written up for that. All right, so here is our outline of all the different patterns of radioactive decay. Alpha decay, we're releasing a helium nucleus, and so the mass number drops by 4, the atomic number drops by 2. Here are the beta decays. Let's see, we had to make some changes here. And so for beta decay, I want to get a plus sign here to charge balance. And for beta plus decay, I want to get a minus sign here to charge balance. And so I'm not confusing myself with electron capture, I'm going to cross out the electron on that side. And then everything looks pretty good. For the gamma decay, we're going from some excited state to, well, it wouldn't have to be the ground state, but typically from some excited state to the ground state releases a high energy photon. So I would need to know the energy differences or the mass differences between those two states in determining what the energy of that gamma, of that high energy photon would be. All right, that's an outline of all of our different types of decay. Now, we want to start looking in more detail about half-life and rates of decay for these different sorts of material. So nuclear decay, it's a random process. Now, what that means is it's random in the sense that each nucleus independently determines when it's going to decay. So whether we have a whole collection of nuclei or whether we have the nuclei separated out one, by themselves, they don't influence each other's decay. They all decay statistically just based on probabilities of decay. And so in this case, what they're saying is this is carbon-14, got a bunch of carbon-14 atoms, they're undergoing radioactive decay. Here is a nitrogen-14 that it's turning into. So I'm starting with a bunch of carbon-14s over here. And then one of them decays, and here comes the electron, and the neutrino came out too. And then another one decays, so another electron and neutrino come out. So that's kind of our model conceptually as to what we have going on here. And so that sets up a mathematical formula that we can write down for this. And the mathematical formula that we're going to be working from looks something like this. So what they're saying here is that the number of radioactive decays, dN, that occur during a given time interval of dt depend on the number that are present times some kind of a decay constant. Now the decay constant here is written as lambda, and there's a minus sign in this because the numbers are decreasing. As time goes on, as the decays occur, there are going to be fewer and fewer of the original radioactive sample that we started with. Let's look at another way that this is written up. So maybe we can, I hope this will make sense. So here's our radioactive decay rates. And I'm going to say this is my rate formula. And the rate formula, I'm going to write it as dN dt. I'm going to bring that dt over to the other side and say dN dt is the time rate at which decays are taking place. Now that rate is a negative value, so I got my minus sign in here. And then this lambda, this decay constant, that's something that's going to be different for each radioactive isotope. So each radioactive isotope that we take a look at is going to have a different decay constant that goes along with that. So here's the decay constant lambda. Now let's carry out this integration first of all. So what it's saying is that the rate of decays depends on how many are there. What does that mean? Let's say we have a sample with 100 radioactive nuclei and that we have a decay rate of, every second or so, one of those decays. Well, what happens if I have 10 times as large of a sample? Instead of having 100, I have 1,000 present. Well, if these are decaying at 1 atom per 100 per second, this sample is going to decay at 10 times the rate because there's 10 times as many that are there. So that's what this statement is saying, is that the number of decays we see will be proportional to sample size. And that means that the decay rate's independent of, individual decays are independent of what other numbers are around. The decay rate that we observe is just the combined rate of a bunch of individual atoms undergoing radioactive decay. So I can bring the n over to this side take the dt, move it over to the other side, and then I can carry out integrations. So what I'm going to have here is dn over n integrated from a starting value of n naught, that's my original sample size, the number that I'm starting with, to some later value. So I'm going to treat that other n limit as a variable. And then on the other side, we're going to be integrating time. Now, lambda is a constant value. That comes outside of the integration sign. So I've got minus lambda times the integral of dt, and that's going to be evaluated between 0, when we hit that stopwatch, until any later time. That gives me a formula of ln, n over n naught, is equal to minus lambda times t. So a couple more lines of algebra. I'm going to exponentiate both sides. I'll exponentiate this. When I exponentiate this, it undoes the natural logarithm. And so I'm left with n over n naught equals e to the minus lambda t. And then finally I can put it in this form, which says the number of remaining radioactive nuclei that I have as a function of time depends on how many I started with multiplied by this exponential factor. So that exponential factor tells me that as a function of time, what I'm going to see is this exponential drop-off in the number of remaining radioactive nuclei in my sample. So now it's an exponential drop-off, and the formula we came up with shows this exponential drop-off in terms of base e. And base e is the natural base to work with for exponentiation. But we could have used base 2 instead. We didn't have to use base e. If we had used base 2 instead of base e to represent this exponential drop-off, then we would introduce the idea of what's called a half-life. Now, taking a look at the diagram that we have right here, here's the number we started with. It's dropping off exponentially. At some point, it's going to cross a point at which the remaining sample size, it's only half of what we started with. And at that time, we refer to that as the half-life for a material. So half-lives are really intuitive, I guess, and that's why we do work from half-life a lot. If you look at Appendix F, Appendix F, your friend, where you find all the data for all these individual isotopes, what you'll find is when they look at a radioactive isotope, they'll tell you, is it alpha decay, is it beta plus, beta minus, beta neutral, and then they'll tell you what the half-life is. Now, a half-life is not in base E, it has to be switched over. So the way this works is, we've got this item that was referred to as a decay constant. Now that's what we started with when we were carrying out this integration and came up with our formula. But now I want to look at two alternate ways to keep track of this. So we often, instead of using a decay constant, we work in terms of its inverse. And the inverse is referred to as the lifetime. So think of this, in physics 4b, these were the time constants. Remember RC circuits and RL circuits, they had time constants to them. So this is the equivalent of time constants back into our time-dependent circuits. And they had these exponential factors, not in terms of a decay constant, but instead written in terms of a time constant. So the time constant for radioactive decay is referred to as the lifetime for that isotope. Now remember, lifetime doesn't mean that once that time has transpired, everybody decays. It's just a statistical measure of, on average, how long do we have to wait to see a decay take place. Okay. Uranium-238, for example, has a half-life of 4.6 billion years. It doesn't mean you have to wait 4.6 billion years for that to decay. It's just a statistical sort of thing. So anyway, if we have a sample of radioactive materials, they're just constantly decaying, and we can keep track of that rate, either in terms of the decay constant or in terms of, this is my personal preference, is the lifetime. It has units of time itself. And then we already discussed half-life a bit, so how are these things all related? Well, the half-life is related to the decay constant by the ln of 2. If you remember back to your math classes, how do I switch from representing exponential functions in different bases? And we can do that by using logarithm values. So that ln of 2 factor is in there because we're switching out of base 2 into base e. So those are our conversions. Now, again, my personal favorite is working in terms of the time constants. And so I've drawn out the graphs for this decay process in terms of using the time constants. Now there's a second equation that we can also, this is going to be very important for us. In addition to keeping track of how many radioactive atoms I have in my sample, I also want to be able to keep track of the rate at which they're decaying. So if I have a sample, and I want to know how many of those are radioactive, I could count them. Now that would mean going in and somehow identifying which atoms are radioactive and or nuclei are radioactive and which ones are not. That sounds like that's not a very good approach. So what we can do instead is we can get like a Geiger counter. We can take the radioactive sample, put a detector nearby, and measure the rate at which it's decaying. It turns out that if we measure the decay rates for these radioactive materials, we can do some simple calculations and determine what the sample size is for that radioactive isotope. So here's the idea. We had something where we went through and solved for how many radioactive atoms we have. What we can do to turn this formula into a decay rate is I'm going to call that big R, and I'm going to define that as the absolute value of dn dt. Now dn dt itself is a negative value. That's a rate at which things are decaying, the rate at which n is decreasing. But I want a positive value. I want something that tells me how many decay particles I'm going to observe per second. And so when I carry out this, what that's equal to is my decay constant times n naught times e to the minus lambda times t. Well, everything that we have right here then looks the very same as the formula before. That's how exponential functions work. So I've got that exponential factor is still there. And if I take lambda times n naught, I could define that as my starting decay rate. So the same way that the number of radioactive nuclei in my sample could be written as an equation of exponentiation in terms of a time constant, I've got an identical graph, but this one is in terms of decay rate. So this one tells me the rate at which things are decaying. This one tells me how many are currently present. So between this formula and this formula and this graph, and these two equations that allow us to switch back and forth, you can pretty much solve all of the homework problems, all of the examples and the problems on midterms and everything that's going to get thrown your way. If you really understand how these two graphs and equations and these are interrelated, you're going to be fine. So at any instant in time, the rate can be calculated by taking n over the time constant. That's how these two formulas are related. And that says when I'm starting off, that same relationship holds, that the initial rate is n naught divided by the time constant. All right, that's a lot to take in. I'm going to take a bit of a break. Probably in this next lecture, what we'll do then is we'll review this quickly, and then we'll move on and look at a good number of numerical examples and get some practice working from all this.